As you know, my name is Jack, and for the past 4 months, I've been working on my master's thesis with Professor Ignacy Casanova on exploration and utilization of lunar resources affected by space weathering. So, oh, sorry. So in this presentation, I'll give a brief introduction on what consists in this project. I'll also discuss briefly the lunar surface, space weathering in regards to what was involved with space weathering and how it interacts with the lunar surface. A brief description on the lunar simulants that were implemented in this project will be given. And with regards to the experiments that were conducted within this project, I'll include hydrogen reduction, the SEM characterization, analyzing the UV to the visible spectrum of the reflectance spectra, and finally a MOSPER analysis. And then to conclude this presentation, I'll give a brief conclusion on this project and presentation. So let's begin. So within this project, effectively what we're looking at is to analyze the optical spectra of the lunar simulants in order to identify any space weathering products that have been formed. So why this project? Well, by being able to analyze the optical properties, it will go hand in hand with remote sensing. And implementing remote sensing, we'll be able to locate resources efficiently. And with reference to the Chandrayaan-1 satellite, this had the capability of viewing 25 to 50% of the lunar surface. And this was been able to accomplish within its project lifetime of 2 years. This is a massive proportion of the lunar surface. When comparing this to factors such as tools such as rovers or manned missions in order to analyze the same amount of area, clearly implementing remote sensing would be the more cost-effective, and it would take less time in order to analyze the same amount of area. By completing this project, this will be able to aid in missions such as NASA's Artemis mission and the Lunar Gateway project. By being able to locate the lunar resources, we'll be able to identify the optimal locations and where we can extract lunar resources, which will greatly benefit these two missions of the Artemis and Lunar Gateway project. Both of these missions are seeing that manned crews are going to the surface of the moon, so being able to utilize and optimally extract the lunar resources will be is greatly needed. Ultimately, this is an essential step which will see that the construction of a self-sustaining off-world base to be accomplished. So on top of this, so by analyzing the optical spectra, we will be able to create a model that will be able to interpret what is the products, what is the substances which are present on the lunar surface. And to demonstrate the power of these optical models, we can see in this image in front of you, a global view of the lunar surface. This is plotting the iron oxide which is present on the surface of the moon. And as we can see here, there's clear areas where iron oxide is at its densest. However, this was developed in 1998, and the iron oxide is a substance which is unaffected by space weathering. So therefore, we need to look at a model which takes into account space weathering. And for example, the Hapke's radiative transfer model does this. This model was developed by Hapke in 2001, and since then has been progressively improved throughout the years, including up until today as well. However, this model only uses the reflectance spectra, the reflectance within the visible and near-infrared regions of the electromagnetic spectrum. Discussed in this study is the effect of implementing smaller wavelengths in order to gain a better understanding of the substances that are on the surface of the particles that are present on the lunar surface. Effectively, this will be later explained in this presentation. However, the act of being able that smaller wavelengths are able to have a greater view of the substances on the surface of these particles creates gives us the backing in order to progress with this project, in order to view the optical spectra within the UV region. So within the lunar surface, so what is on the lunar surface? Well, the lunar surface is made up of lunar regolith, a very fine powder, which is made up of different rocks, and effectively, with regards to its particle shape and particle size, it's effectively reached a steady state. This is from the repeated bombardment of micrometeorites, an event which is also considered as a space weathering, which again will be discussed later as well. By being effectively reaching this steady state, this means that its particle shape and particle sizes are all within a narrow band and relatively similar to one another. In this table, we can see the chemical compositions of what is present within the lunar regolith. As we can see, there's three different types of lunar soils. We have the mare, highland, and basin ejecta. By viewing this image here, we can see that the mare represents these darker proportions of the moon's surface. These highlands represents this lighter area, and is effectively more of a rough terrain due to all of the impact craters from meteorites. And then basin ejecta corresponds to the debris which is ejected from these craters once these meteorites are impacted. It must be said that there's a lot of other substances and oxides that are present within the lunar regolith, but for the sake of this project, we're only going to be viewing the iron oxide. And as we can see here, that within the mare, this contains the largest amount of iron oxide when compared to highland and basin ejecta. The highland contains the least, and the basin ejecta acts as a middle ground between these three soil types. So space weathering. Well, space weathering generates a dynamic environment on the surface of the moon and comes in the form of solar winds and micrometeorite impacts. Effectively, these two events both alter the microstructure and the chemistry of the lunar surface. But more specifically, how does this actually alter this lunar surface? Well, it comes in the form of rims. If we take this figure that we see on the right here as being a particle, we can see that this area shaded in blue is known as a host grain, effectively the original particle. It is then coated within this rim, which is effectively the surface of this particle, which is exposed to the space weathering. These rims come in four different types. We have the amorphous rim, which is generated by a radiation of high flux, low energy ions from solar winds, effectively sputtering the chemical compounds on the surface of on the surface of the lunar regolith, which effectively reduces the iron oxide there, and within this amorphous rims, we can see metallic iron being present. We also have a vesicular rims. These consist in these rims, there's tiny vesicles which tend to be in the region of less than or equal to 50 nanometers, and they tend to be within a 100 nanometer range surrounding the host grain. And as we can see here, that is generated. These vesicles are generated by the embedment of solar wind gases during a pulse heating event. We also have an inclusion-rich rims. These rims appear by the settling of impact-induced vapors. Effectively, this goes hand in hand with vesicular rims, as once a micrometeorite impacts, it creates it extremely heats up the surrounding areas and the soils, effectively melting the soils and creating a vapor. The embedding of these solar winds, effectively, more essentially, the hydrogen ions being present. The hydrogen ions are being present within this vapor, and this vapor is has extremely high temperatures, effectively creating an extremely reductive environment. As the iron oxide, compared to the other oxides which are present within the lunar regolith, has the weakest binding energy. The hydrogen acts as a reduction agent, which then reacts with the oxygen, which is attached to this the iron element, effectively reducing the iron down to its metallic constitution. Therefore, it then once it condenses, the vapor then settles, and we have this glass-like material, and we will see the metallic ion being present within this glass type substance. We finally have multiple rims, and multiple rims are a combination of amorphous rims and inclusion-rich rims. Essentially, the amorphous rim is on the inner layer of these particles, and then is coated by the inclusion-rich rims. And as I stated with the reason of these appearances, the inner layer of the multiple rim corresponding with the amorphous rims is generated by irradiation erosion, and then the outer layer appears due to the settling of impact-induced vapor. So with regards to lunar simulants, 2 lunar simulants were analyzed in this project, JSC1 and FJS3. Starting with JSC1, it was developed by NASA Johnson Space Center, hence the abbreviation of JSC. Effectively, it was developed to replicate the physical and chemical compositions of the lunar mare. However, not all characteristics can be replicated here on Earth. As I previously said, the glass-like substance, which is produced by the condensation of the impact-induced vapor, contains metallic iron. This content of iron is very hard to replicate here on Earth. And this glass is known as aglatinite glass. And in this table here, we can see the chemical composition of this lunar simulant. It must be noted that we can see an Fe2O3, also known as hematite. Hematite corresponds to the third stage oxidation of iron, which is not really present, on the moon, as for the reasons of space weathering and the events that occur on the lunar surface. Effectively, the lunar surface is an extremely reductive environment. So having iron at its third oxidation level is very uncommon, even though there has been studies recently to suggest that hematite has appeared in the high altitudes of the moon. Now moving on to FJS3. FJS3 was developed by Shimizu Corporation. This is a Japanese corporation where they developed three types of FJS simulants: FJS1, 2, and 3. These differ between their mineralogy. With regards to FJS3, it consists of 83% basalt, 11% overline, and 8% ilmenite. And this differs from the other two, where the FJS1 is 100% basalt. Not much information is given on FJS simulants. However, one thing that can be said for certain is that this simulant is far finer than that of JSC1. And demonstrated here, we can see that the bulk chemistry of this FJS3 lunar simulant. We can see as well that there's a higher percentage of titanium dioxide, which corresponds to the 8% of ilmenite. And again, there's that hematite which is appearing. But with regards to this project, we can disregard the ilmenite. Now, moving on to the experiments which were conducted within this project. The first experiment that was conducted was hydrogen reduction. But what needs to be considered? Well, many studies have been implemented in doing hydrogen reduction. However, these studies have the aim of obtaining water and oxygen. However, there is a correlation between this. When reducing iron oxide with hydrogen and even ilmenite, which we can see as this iron, titanium, and oxygen compound, the two main compounds which are produced, the two elements, as well as metallic iron and water. In regards to ilmenite, there's titanium dioxide as well. When referencing the previous studies that were researched in this throughout this project, it was decided that 600 degrees Celsius, 800 degrees Celsius, and 1000 degrees Celsius were the three temperatures that were going to be used within this study. This is because all three of these temperatures are known to be able to reduce the lunar simulants, and they have less of an impact with regards to sintering and clumping. With regards to the duration of this reduction, the simulants will be processed at these temperatures for 2 hours, and then they'll also be processed at these temperatures for 4 hours as well. So moving on to the characterization. Using the scanned electron microscope, we used 3 different types of detectors: detecting secondary electrons, backscattered electrons, and then X-rays as well. The secondary electrons allowed us to view the topography, but more importantly, the backscattered electrons allowed us to locate areas where reduction may have occurred. And here's the first image of the backscattered image we can see. And the image on the left, we can see that there's a brighter particle, which is the area which is in question. And then to provide a reference, we've also viewed on the right, you can see that we've viewed the darker particle as well. Essentially, by viewing the elemental compositions of these particles, we can see that this brighter particle on the left has a much higher presence of iron with low amounts of oxygen and silicon. And when viewing this darker particle here, there's a substantially more amount of silicon when it compared to iron, and there's an increased amount of oxygen there as well. So what we can get from this is that by viewing these images, we can see that the brighter areas within this backscattered images correspond to areas where reduction may have occurred, and the darker areas correspond where reduction is most unlikely to have occurred. So moving on to the second area that was analyzed, as we can see, there's a general increase in magnification on this one particle. This particle is fairly bright, and then it starts getting darker and darker. And by the image on the far right, we can see there's only tiny abundances of these brighter areas. Giving more information is these elemental compositions. So when viewing the image on the left, when viewing this image here, we can see that there's a massive amount of iron here with very low amount of oxygen and silicon here as well. So just by viewing this image here, we could easily infer that this particle is in fact a metallic iron particle. However, once increasing the magnification, this isn't the case, as silicon and oxygen increases here in this middle image. And then moving on to the right, you can see that silicon is far greater than that of the iron element. So essentially what we can get from here is that when we're viewing this particle in a lower magnification, these smaller abundances of iron here will effectively act as one, coalesce together and effectively act as one greater particle of iron. This is a factor that could have a major effect on the analysis of the optical spectra, as it's been determined that metallic iron has a massive effect on the optical spectra of the reflectance that's produced. Here we can see there's two different images of ilmenite. However, these aren't the two same. They're not the same samples. The one on the left is of FJS3 being reduced for 800 degrees Celsius for 2 hours, and the one on the right is FJS being reduced for 800 degrees, however, for 4 hours instead. Effectively, as we've already established, we can't really gauge a good enough approximation on what is occurring on this left side of on this image as we see on the left. However, by viewing the elemental compositions, just by seeing these two images, we can see that the amount of titanium in the image on the right is far less than that on the left, which is to be expected, seeing that has been reduced for that of double of its time. So another tool that was implemented, this is the same image that was the same sample of FJS3 being reduced at 800 degrees for 4 hours. We can now use a line spectra. Effectively, this line spectra allows us to obtain the elemental compositions all across this line. So this includes this dark area here and these bright areas and so on and so forth. Here we can see the spectra that has been produced. And down here is the legend of what each of these colors correspond to. So we can see that this blue spectrum represents iron, the green spectrum represents titanium, and the yellow spectrum represents oxygen. We can see, referring to this middle image here, we can see that in the brighter areas, there's a significant increase in spike of iron and very low amounts of titanium and oxygen here. And then when viewing this dark air patch here, there's a much lower amount of iron here with an increase in titanium and a fairly standard plateau of oxygen here as well. Effectively, we can see that on this ilmenite ilmenite particle, effectively what has happened is that this ilmenite is now covered with metallic iron, which is something that was a surprise when viewing in the SEM characterization. Finally, with regards to this, regards to the characterization of these particles, there's one interesting fact that needs to be considered, and this is this image right here. Another tool differing from analyzing a single point and just a line is the fact that we can analyze this entire picture here with regards to its elemental composition. And we can see the composition here on the right. The major thing that we should take from these images is the fact that iron, the concentration of iron is significant on this right-hand side, where locations where oxygen is not present at all. So what we can say from this is that this particle has been fully reduced down to metallic iron. It must be stated as well that this sample gained from here is of JSC1, which JSC1 is entirely made up of silicate minerals. So without the addition of ilmenite or any other types of minerals, we have confirmed that the reduction of just a lonely silicate mineral has occurred, and metallic iron is present within these silicate minerals. So this concludes the SEM characterization, and now we move on to the UV to vis spectrometry. So these are the two reflectance spectra that were gained when viewing the JSC1 when reduced for 2 hours and then reduced for 4 hours. We can see that there's an increase in reflectance for the 1000 degree sample when run at 2 hours, which again referencing an image of how metallic iron impacts the reflectance. Once metallic iron is greater than 100 nanometers, it starts to increasingly get more and more reflectant. So this increase in reflectance here could correspond to the presence of metallic iron being greater than 100 nanometers in size. However, as well established in the SEM characterization is that if the abundances are close enough together of metallic iron, it can act as a larger area and effectively just a large particle of metallic iron. But one thing consistent through both of these images is that the reduction of this reddening gradient that we see here, which we can see in the JSC1 4 hours, there's a gentle decrease until it reaches a spectrally neutral point by the time by the 1000 degree reduction sample. Again, we can see the same characteristics of the reflectance that we see in the JSC sample. Is that the 600 degrees sample and the 800 degrees when reduced at 4 hours both increase reflectance. But consistent with the JSC1 is the reduction of the reddening gradient, something that is consistent throughout all of these samples. One thing that needs to be noted as well is that conversely to the JSC sample when ran at 4 hours, the FGS3 sample here still has a reddening gradient and hasn't reached a plateau when ran at 1000 degrees Celsius. And this is because of the presence of titanium dioxide, another product when reducing ilmenite by hydrogen. And effectively, it was found that titanium dioxide is extremely invisible in the UV region. However, within the visible and near infrared region, it becomes extremely reflectant. So therefore, that is why we're still seeing this reddening gradient on the image that we see on the right. So as well as I established that consistent through all of these images is the reduction of the reddening gradient. So therefore, we aim to quantify this reduction. And to do so, we viewed that this area here, this gradient here was at its steepest and ultimately had the majority of the effect occurring here. So therefore, we took the reflectance at 250 nanometers and 350 nanometers as well. And this is what the plots that were produced. On the left, we have the JSC plot, and on the right, we have the FJS plot. We can see that as we're increasing the temperature, this reddening gradient is indeed decreasing. However, there's points where the reddening gradient is above that of its previous sample. Ultimately, from this, we then aim to fit a curve to this these plots in order so that a future interpolation can be conducted in order to determine the red and to predict the reddening gradient when specifically specifically reducing the simulant at a given temperature. And here's the curves that were fit. As you can see, they're polynomial curves. These curves were picked because of the increases that we see here and here as well, as opposed to just fitting an exponential curve. In some of these plots, it provides a relatively accurate representation of the experimental curves. And we see in the bottom right, it's relatively accurate. However, there are areas where there is a large amount of error that we can be seen here, 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 and here. Ultimately, this could be improved better by reducing more simulants at a more variety of temperatures. By doing this, we'll be able to gain more data points, effectively being able to understand the correlation much more and being able to fit a much more accurate curve equation to the correlation that should be seen. And then to finalize these experiments, we conducted a Mossberg analysis. Effectively, the Mossberg analysis utilizes a radiative decaying object. In this case, the source was a cobalt 57, and the catch with of using a radiative source is that it only emits a particle that of one energy. So therefore, we moved the source towards the sample and away from the sample, which corresponds to these velocities of the source that we see on this x-axis. Effectively, by moving this, we're implementing redshift and blue shift on these particles, on the particles' wavelengths. And by changing these wavelengths, we're altering the energy of these particles. And then that's how we're being able to gain the spectrum of the samples. It can be seen as well that we only utilize JSE1 at 1000 degrees for 240 minutes and the unprocessed JSE1. This was just solely down to time. However, this does give a good basis for viewing the increase in content of metallic iron, as it was recorded that there was a 30% increase in the metallic iron that was present when comparing the JSE 1240 to the unprocessed JSE 1. By implementing further analysis, the quantification of the metallic iron content will be able to become more accurate, and we'll be able to analyze the other samples as well. So, in conclusion, ultimately we found that the hydrogen reduction process did indeed mimic the products produced by the space weathering interactions that occur on the surface of the moon. And also, this study provides the basis to further develop a model that will approximate the metallic iron content within the lunar surface. But what factors should be furthered within regards to this model? Well, the first one, as I previously said, would be to process the simulants at more reduction temperatures. As I said, this would increase the amount of data points, improving our understanding of the correlation between temperature and the reddening gradient. In addition to this as well, further Mossberg analysis will need to be completed in order to better quantify the metallic ion content. When both of these two factors would be completed, we would be able to view the reddening gradient on the y-axis with the quantity of iron on the x-axis as well. This will be able to benefit the modeling of the lunar surface substantially. So this concludes my presentation. Thank you for your attention, and I'll be happy to answer any of your questions.